Hello, everyone. Today I'll be presenting the paper LightGlue, local feature matching at light speed. So LightGlue is a deep neural network that learns to match local features across images, and it provides effective and efficient improvements from the previous state-of-the-art model, which is SuperGlue. We will look at it through these three sections: the introduction, strengths and weaknesses. So to overview, the LightGlue is a model that that is from the field of image matching, and some of the challenges in the field of image matching is like the two main challenges are uniqueness and robustness. Uniqueness speaks to reliably describing each point or correspondence in conditions which have in basically challenging conditions conditions having symmetry, weak texture, and some conditions which have light and viewpoint variations. And as for robustness, it includes rejecting outlier correspondences due to occlusions or non-repeatability or missing points. And a good model should be discriminative of that fact. And SuperGlue is one such state-of-the-art model which was long unrivaled in this field in sparse matching, and it provided great visual localization results in challenging conditions. Um so SuperGlue introduced a new paradigm by considering both images at the same time to jointly match sparse features and to reject the outliers. It was the first of its kind, and it uses a transformer model to leverage its capabilities for the problem of optimal transport, which has a heavy computation of row and column normalization, which is actually the main bottleneck of SuperGlue. So in transformers, absolute sign or learned positional encodings were initially used, but after recent advancements in transformers, LightGlue and other models have shown that these absolute point position encodings tend to be forgotten in the deeper layers of the network. The positional encodings here is like the normalization of coordinates while also retaining the aspect ratio and then projecting those into frequencies using linear and other transformations. And point reprojection using camera and depth is a point that SuperGlue uses to calculate the ground truth, and that is ultimately used to classify the points as outliers or inliers. And despite all these advantages, it has large computing resource requirement, and because it's a transformer based model, SuperGlue is notoriously hard to train, and it requires resources that are inaccessible to most of the population. It uses the sinkhorn algorithm for the purpose of the optimal transport problem that we talked about just now, and which is very memory and computationally expensive. And it also uses the dustbin mechanism to reject outliers. But in the process of doing that, it entangles the similarity scores of the other points and yields suboptimal training dynamics. So we'll see what similarity and some other concepts are. And it only has final layer predictions. So there are no intermediate predictions of any sort. And that turns out to be what LightGlue takes advantage of. So LightGlue mostly follows SuperGlue for the supervised training setup. For example, it does pre-training on synthetic homographies to learn to extract correspondences. And then it trains its classifier. And since SuperGlue and its use of the original transformer model, several other works have used improved transformer techniques, and similarly, LightGlue uses efficient self-attention called flash attention for their optimized model, which is also their best performing model. And relative positional encodings. So in this, unlike SuperGlue, it uses pairwise similarity and matchability matrices, which is also called bidirectional attention. And then a combination of these matrices is used for the prediction. So similarity here is nothing but if a point is similar to another point, and in self-attention unit, basically inside the same image. And for matchability, if the points are matchable, or the likelihood of a point having a correspondence in the other image, which basically is used in cross-attention. So faster inference on easy images, the adaptability. This is also a novel approach of the authors. They talk about adaptive depth and width. So in depth adaptivity, the network uses early predictions to exit and not to use the entire network depth. And in width adaptivity, the network only searches for correspondences within a specific region using a technique called point pruning. And so it doesn't have to search through the entire image. And using these novel architectural or other modifications and insights, LightGlue is more memory and computational efficient than SuperGlue. It's more accurate and it's much easier to train. And most important of all, it opens up exciting prospects in latency sensitive applications like 3D reconstruction and SLAM. So architecture. So in the architecture of LightGlue, it has 9 transformer layers, and which process a pair of 2 images jointly, and each layer is composed of self and cross attention units that update the representation of each point. And in the self attention unit, there's a multi-layer perceptron that updates a message that is calculated from a source image. And in the self attention unit, each image pulls information from points within itself. And similarly, on the same lines, in a cross attention unit, each image pulls information from the other image. And there's a score calculation using projection matrix in the attention units. So in the self-attention unit, instead of using absolute positional encodings like SuperGlue, the LightGlue architecture uses rotary embeddings, something called rotary embeddings. And it's also on the same lines as the recent advancements in transformer techniques. And it makes use of the positional encoding to gather points in a learned relative position. So basically, within the same image, where is a particular feature with respect to other features, and it turns out these rotary embeddings do not affect the time or the complexity of the model, but they do improve the speed and accuracy. And these rotary embeddings are only computed once and then cached to improve accuracy. And in the cross attention layer, we have a concept called a bidirectional attention, where like we just discussed, we get the 2 images and we use them to calculate scores with respect to each other. and they also use a confidence classifier along with something called similarity and matchability matrices. And as we talked about it before, the similarity matrix is nothing but where if a pair of points I j that will yield a correspondence when both points are predicted as matchable, and when the similarity is higher than any other point, then those points are similar according in the similarity matrix. And as for the matchability matrix, it's used in accordance with the confidence classifier, and it tells the network whether a point is matchable, or basically does it have a match or correspondence in the other image or not. Uh, and combining with this, there's a exit criteria. So for the exit criteria, it uses a confidence threshold and a confidence ratio. And if this confidence ratio is sufficient, or if it's reached for all points in the image, then the network decides that it's time to stop the inference, and it stops at early stages for easy images. So we'll see the example of those in the later slides. And it does that through each layer, through the entire network, with each layer, with all the 9 layers. So the authors are pretty abundantly clear that LightGlue performs better and in the speed versus accuracy trade-off throughout the paper. They point several times that it outperforms SuperGlue, which is the state-of-the-art sparse matching model, and LOFT, which is a dense matcher, and it works somewhat differently to LightGlue or SuperGlue, because it uses dense grids to match the features instead of sparse regions in an image. And similarly, match former, another dense matcher. So we can see that even with only 3 layers of LightGlue, it has tremendous advantage in the aspect of speed. But lacks the relative pose accuracy. And as the network gets deeper, it also increases in its accuracy. And the authors claim that their optimized model, which is their best performing model, outperforms all other models, the dense or sparse matchers, in many of the applications, which include homography estimation, outdoor visual localization, or even relative pose estimation. So we'll talk about some key strengths of LightGlue. As we said earlier, the authors mentioned that the model is depth adaptive as well as width adaptive. Depth adaptive in the sense that the network has a sense of exiting early and not using the entire network, and early discarding. So basically, these features of the model work in accordance with each other. They basically work hand in hand to the advantage of the model. Early discarding is nothing but point proving, as we will see with some of the results. So here, depth adaptivity is shown. So you can see for the first example, the 2 images are very similar, or basically they do not have much variation in the rotational sense. They just have some translational variation in X and Y axis. And we can see that there are a lot of points or key points to be matched in most of the region of the images, in both images. So this is classified as an easy prediction and easy inference, and the network stops after 3 layers only, much faster and much quicker, and within 3 layers. And in contrast to that, for a hard example, you can see in the second example that there is light variation, there is viewpoint variation, and the textures are way better seen in the second image than in the first, but it's still able to the point correspondences, but it does that after 8 layers. It requires the self attention and cross attention units of the deeper layers to predict the matches. And point pruning is nothing but the width adaptivity that the authors talk about. So basically, in the first image, you can see the blue points are the ones that have a match in the second image, and the red points, the red region is basically the region which the model need not look into. And this happens to be a key feature of the model, because what happens is, if you look at the first image, there are almost half of the points are in this blue region, and the other half are red, orange, or yellow, which are non-matchable points, which are not found in the other image, and those are basically useless. So that those points the model calculates early out those points for the sake of computation, and it turns out that the improvement is in order of quadratic order. So which this exact point turns to be a bottleneck for SuperGlue. It turns to be a key feature for LightGlue. So we'll look at some easy, medium, and difficult cases, as the authors have pointed out. So point pruning, you can see, as with the previous example, only the points which are matchable, those are highlighted in blue. And these are relatively easy cases because they don't have much rotational or translational variation, as well as the light is pretty much similar in these three cases. And so the network only looks where there are matchable points, and then matches those points. So in medium cases, we can see directly that in all first and second example, we can see that almost half of the image regions are not taken into consideration for the computation of correspondences. And this is the use of having point pruning at early stages. And it basically benefits the network in terms of efficiency. And you can look at the third example for so in the third example, you can see the leftmost wheel of the motor, which is not visible entirely in the second image, and so those are not taken into account in the matchability metrics, and only the green ones are taken into account, and those matches are shown. And in the case of difficult matches, so you can see a lot of rotational as well as translational variation here. Also, the light intensity difference is also there. So, and still the network is able to calculate a pretty good amount of correspondences, considering the minimal overlap between the input image pairs. So key weaknesses of the LightGlue model. So for a model which has to which should open up exciting prospects in the fields where latency sensitive applications are present, they do not provide much real-time testing that they have done. They only provide datasets like Megadepth and Oxford and several other datasets that are used in the image matching field. But if they had included some real-time testing, then it made a stronger and bigger case for its use in in such applications. Improvements in architecture. So the authors themselves mentioned that the improvements that they have made over SuperGlue, that they have made those improvements where the SuperGlue bottlenecks and but it turns out those are the same bottlenecks, not the same, but those are the same points where LightGlue also faces bottlenecks, such as a double softmax layer, which is used in the classifier. It turns out that is a bottleneck, and so such small improvements in architecture could go a long way to make the model even faster. And the authors also point out, for indoor visual localization, it kind of matches unrelated features. You can see the two images are different in this case, and it's still trying to match something there. And in contrast with their testing on outdoor visual localization, where it outperforms SuperGlue and the other models, if within the indoor visual localization domain, it struggles somewhat. So the training details, they've given some training details here, and the pre-training on synthetic homographies, it's similar to SuperGlue. It's where they apply homography to the edge patches data set, and they then train the model to make it learn the correspondences within those synthetic homographies. And it turns out that that plays a key role in the model learning to match with the correspondences. So basically tuning the learning rate and adding more points, grading, checkpointing. These are some of the points with others like learning rate decay, mixed precision, a bigger batch size. And these are the points they use to optimize training. So they also train the LightGlue model with feature descriptors like superpoint, SIFT, and disk. And in the image matching challenge 2020, they have used their model with disk, and they have outperformed the SuperGlue plus superpoint model by 2.3%. And so basically they use these three feature descriptors to train their own network. And the point that they mention a lot is efficiency and accuracy. So they train their model within 2 GPU days, within 40 to 50 epochs, unlike the 7 days that are required for SuperGlue training, which is quite a lot. And they use the concept of caching with respect to various parameters. So they also require 200 GB of ROM, and they have trained all this on a single RTX 3080 GPU with 24 GB VRAM. So our conclusion for the paper is that LightGlue is a promising new network in the field of image matching, and it certainly does seem to be a precursor to some great latency sensitive applications, and it can certainly be used for that. When it has some more improvements made in accordance with those fields. And but for the testing and evaluation is certainly required for the model to be be compatible with those fields and to be even more robust and faster than right now. That's it for this paper. Thank you. Please let us know if you have any questions. If there are no more questions, we can conclude this. Thank you. Thank you so much.